In the previous video, we saw that sine of alpha plus beta can be expanded as sine of alpha cosine of beta plus cosine of alpha sine of beta. In this video, we're going to discover how sine of alpha minus beta can be expanded, also cosine of alpha plus beta, and cosine of alpha minus beta. We're going to prove each of those equalities in two ways. So for the first equality, sine of alpha minus beta, the first way to prove it is to take this equality and replace beta with minus beta. Essentially, we get sine of alpha plus minus beta, which is equal to sine of alpha minus beta. And on the right hand side, we get sine of alpha cosine of minus beta instead of beta. And here we get cosine of alpha times sine of minus beta instead of beta. So we get this equality here. But we know that cosine of minus beta equals cosine of beta, and sine of minus beta equals minus sine of beta. So we can rewrite this expression as sine of alpha cosine of beta minus cosine of alpha sine of beta. And so we got the formula for sine of alpha minus beta. You can notice that this formula and this formula only differ in two places. The plus here became a minus and the plus here became a minus. The second way in which we will derive sine of alpha minus beta is illustrated here. Suppose that this is a triangle with a circumradius of 1/2, and the angles of this triangle are beta and 180 minus alpha. Therefore, the third angle must be alpha minus beta. From the law of sines, we can find that this side equals 2 times r times the sine of beta, but 2 times r is always 1, and so this side has length sine of beta. Similarly, this side has length sine of 180 minus alpha, and this side has length sine of alpha minus beta. Now from this right-angled triangle with hypotenuse equal to sine of beta and angle alpha here, we get that this side equals sine of beta times the cosine of alpha. And from this right-angled triangle with hypotenuse sine of 180 minus alpha and angle beta here, we get that this side equals sine of 180 minus alpha times the cosine of beta. And therefore, sine of alpha minus beta can be expressed as this whole segment minus this small segment here. So sine of alpha minus beta equals sine of 180 minus alpha cosine of beta minus sine of beta cosine of alpha. So we got this equality here. But now note that sine of 180 minus alpha equals sine of alpha. And so we can rewrite this equality as sine of alpha minus beta equals sine of alpha cosine of beta minus cosine of alpha sine of beta. And this is exactly the same expression we got here. Now let's try to derive what's cosine of alpha plus beta. I'm gonna take sine of alpha plus beta, this formula, and substitute beta with 90 plus beta. Then we got this equality here. Sine of alpha plus beta turns into sine of alpha plus 90 plus beta, cosine of beta turns into cosine of 90 plus beta, and sine of beta turns into sine of 90 plus beta. Oops, but we forgot what sine and cosine of 90 plus beta is. So how are we supposed to evaluate that? Well, we can always turn to the unit circle when we don't remember how to evaluate an expression such as cosine of 90 plus beta. We construct an angle 90 plus beta, which corresponds to this point, and so the sine of this angle would be the length of this segment, positive, and the cosine would be the length of this segment, negative. And let's construct an angle 90 minus beta corresponding to this point. This point is symmetric to this point with respect to this line. And therefore, sine of 90 minus beta corresponds to this segment again. So sine of 90 plus beta equals sine of 90 minus beta. Also, cosine of 90 minus beta would be this length, positive, and it equals this length, but this length is in the negative direction. And so, replacing sine of 90 plus beta with sine of 90 minus beta, cosine of 90 plus beta with cosine of 90 minus beta negative, and sine of alpha plus 90 plus beta, which is 90 plus alpha plus beta, we can replace it by sine of 90 minus alpha minus beta. We get this expression here. And now we know that sine of 90 minus beta equals cosine of beta, and cosine of 90 minus beta equals sine of beta, and sine of 90 minus alpha minus beta equals cosine of alpha plus beta. And so the left-hand side becomes cosine of alpha plus beta, then this here becomes cosine of alpha cosine of beta, which is here, and this part becomes minus sine of alpha sine of beta, which is here. And that's how we got the formula cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. Here's the second way we can derive cosine of alpha plus beta. Suppose we have a triangle, acute angle triangle with angles alpha, beta, and gamma, and suppose this point here is its orthocenter, so this is an altitude and this is an altitude. Suppose that the circumradius of the triangle is 1/2. Then we know that this length is 2 times r cosine of gamma, but since 2 times r is 1, we can say this length is cosine of gamma. We know that this length is cosine of alpha cosine of beta, and we can also find the length of the whole altitude. For example, see that this side is sine of beta from the law of sines, And then, from this right-angled triangle, with hypotenuse sine of beta and this angle is alpha, it follows that the whole altitude equals sine of alpha sine of beta. And therefore, cosine of gamma equals sine of alpha sine of beta minus cosine of alpha cosine of beta. And that's how we get this expression here. But we know that gamma equals 180 minus alpha minus beta. And so cosine of gamma equals cosine of 180 minus alpha minus beta. Cosine of alpha plus beta, we know it equals minus cosine of 180 minus alpha minus beta. And then this here is the same as minus cosine of gamma. And so it must equal the negative of this expression, which is cosine alpha cosine beta minus sine alpha sine beta. And therefore, cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta, which is exactly the same as we got here. Lastly, for cosine of alpha minus beta, we can just take this formula and replace beta with minus beta. Then we get cosine of alpha minus beta on the left-hand side, and on the right-hand side, instead of cosine beta, we write cosine minus beta, and instead of sine beta, we write sine of minus beta. And now we know that cosine of minus beta is cosine of beta, and sine of minus beta is negative sine of beta. So we can replace them and get cosine of alpha minus beta equals cosine alpha cosine beta plus sine of alpha sine of beta. Here's the other way in which we can derive cosine of alpha minus beta. Suppose this here is a triangle with angles beta and 180 minus alpha, such that this angle here is alpha, then this angle must be alpha minus beta. And suppose that this point here is its orthocenter. Also, suppose that the circumradius of the triangle is 1/2. Then, we know that the distance between this vertex of the triangle and the orthocenter equals 2 times r, the cosine of this angle. But 2 times r is 1, so this distance must just be the cosine of alpha minus beta, which is this angle here. From the law of sines, we know that this side of the triangle is sine of 180 minus alpha, which is this angle, and this side is sine of beta. Consider this right-angled triangle. It has a hypotenuse sine of 180 minus alpha, and this angle is beta, so this length here must be sine of 180 minus alpha times sine of beta. But sine of 180 minus alpha equals sine of alpha, and so we can write this length as sine of alpha times sine of beta. Now let's try to find this length. We know that this here is a cyclic quadrilateral because this angle is 90 degrees and this angle is 90 degrees. Therefore, because this angle is beta, this angle here must also be beta. Now we have that this length is sine of beta and this angle is alpha, so in this right-angled triangle, we get that this side is sine of beta times cosine of alpha. And now in this right-angled triangle, where we have that this side is sine of beta cosine of alpha and this angle is beta, we know that this side equals this side times cosine of beta divided by sine of beta. And so this side must be cosine of alpha times the cosine of beta. So finally, we know that cosine of alpha minus beta, which is the length of this whole segment, equals the length of this segment plus the length of this segment. And so it equals cosine of alpha cosine of beta plus sine of alpha sine of beta, which is exactly what we got here. Here's the optional problem. We have a triangle, this is its circumcircle, and this here is its orthocenter. So this is an altitude, this is an altitude, and this is an altitude in the triangle. We connect this foot and this foot with the line and intersect it with this line here. And we continue this altitude until it intersects the circumcircle at this point. This point is the midpoint of this side of the triangle. We have to prove that this point, this point, this point, and this point lie on one circle. And here's the solution. Let's denote the vertices of the triangle by A, B, and C. Let the orthocenter be H. Let this foot of the altitude be F. Let this point here be P, the midpoint of AB, M, and this point E. Let the angles of the triangle be alpha, beta, and gamma. And we know that since this angle is 90 degrees and this angle is 90 degrees, then this quadrilateral is cyclic. Therefore, if this angle is alpha, then this angle here is 180 minus alpha, and so this angle equals alpha. Now we have that this angle is beta, and this angle here must be 180 minus beta, and so this angle is beta minus alpha. Similarly, we know that since this angle is 90 degrees and this angle is 90 degrees, then this quadrilateral here is cyclic. And therefore, since this angle is gamma, then this angle is 180 minus gamma, and so this angle is gamma. Let's denote this point here by Q. And let's note that AC, this side of the triangle, equals 2 times r sine of beta because of the law of sines. And consider this triangle FQB and this triangle ABC. These triangles are similar because they have the same angles alpha, beta, and gamma. The coefficient of similarity is QB divided by AB because QB and AB are corresponding sides in these similar triangles. But QB divided by AB, this is cosine of beta because take a look at the AQB triangle. It is a right-angled triangle with this angle beta, and so QB divided by AB equals cosine of beta. And so, to get the sides of the triangle FQB, We just take the sides of the triangle ABC and multiply them by cosine of beta. For example, FQ equals AC times cosine of beta. And so FQ equals 2 times r sine of beta times the cosine of beta. And now that we know FQ and we know all the angles of this triangle, we can find FE. Note that if this angle is gamma and this angle is beta minus alpha, then this angle must be 2 times alpha to make the angles of this triangle sum up to 180 degrees. And so this side equals this side times the sine of 2 alpha divided by sine of beta minus alpha. And so FE equals 2r sine beta cosine beta, which is FQ, times sine of 2 alpha divided by sine of beta minus alpha. For the length of FP, we know that FP equals FH, because h and p are symmetric with respect to AB, and fh we know equals 2 times r cosine alpha cosine beta. So we got that fp equals 2 times r cosine alpha cosine beta. We know that the length of the altitude, cf, equals 2 times r sine of alpha sine of beta. Finally, let's find the length mf. We know that mb is half of ab, and so mb equals c over 2. So mf equals c over 2 minus fb, this segment. So to find MF, we need to first find FB. But we saw that triangle FBQ is similar to triangle ABC. The corresponding side to FB is BC, and BC equals 2 times r sine of alpha from the law of sines. And the coefficient of similarity is cosine of beta. So FB equals 2 times r sine of alpha times the cosine of beta, which is written here, where from the law of sines I've substituted c over 2 with r times sine of gamma. Now let's try to simplify this expression a little bit, because it's always best when all the segments are expressed in terms of a product of terms and not as a sum or subtraction of terms. So we take this r sine gamma minus 2r sine alpha cosine beta, and we transform sine of gamma into sine of 180 minus alpha minus beta. But sine of 180 minus alpha minus beta equals sine of alpha plus beta. And so this expression can be rewritten as r times, and then in the parentheses, sine of alpha plus beta coming from sine of gamma, and then minus 2 times sine of alpha cosine of beta coming from here. But we know that sine of alpha plus beta equals sine of alpha cosine beta plus cosine alpha sine beta from our formula. And so we can cancel out one term from here, sine alpha cosine beta, with this sine alpha cosine beta. What's left is r times sine beta cosine alpha coming from here, and then the remaining term from here, sine of alpha cosine of beta. But this is also a formula. We know that sine of beta minus alpha equals sine beta cosine alpha minus sine alpha cosine beta, and so we can replace it, and then we get this expression here for MF. We know that this quadrilateral is cyclic if and only if MF times FE equals CF times FP. Essentially, we're expressing the power of the point F with respect to the circle we want to prove. So if we prove this, then we're done. Replacing MF with this expression, replacing FE with this expression, replacing CF with this expression, and replacing FP with this expression, we get that r times sine of beta minus alpha times 2r sine beta cosine beta sine 2 alpha divided by sine of beta minus alpha equals 2r sine alpha sine beta times 2r cosine alpha cosine beta. We need to prove that this equality always holds. But now a lot of things cancel out. For example, sine of beta minus alpha cancels here, 2r cancels here, r cancels here, cosine of beta and sine of beta cancel out here, and so we're left with sine of 2 alpha on the left-hand side and 2 times sine of alpha cosine alpha on the right-hand side. But this equality always holds, because remember that we have the formula sine of alpha plus beta equals sine of alpha cosine beta plus cosine alpha sine of beta. If we replace beta with alpha, we get that sine of 2 alpha equals sine alpha cosine alpha plus cosine alpha sine alpha, which is exactly 2 times sine of alpha cosine of alpha. And so this equality always holds, meaning that this equality here always holds, which tells us that C, M, P, and E always lie on a circle.